In this presentation, you will be introduced to data mining and how it can be applied to meaningful use. Exploratory data analysis is becoming more and more popular in healthcare to find trends and patterns in different data sources. Exploratory data analysis is often referred to as data mining, and this is what I will be calling it through the rest of this course. Data mining is considered the art and science of intelligent data design. The aim of data mining is to discover meaningful insights and knowledge from the data. In this class, we'll be exploring data mining from two different angles. The first lecture focuses on analyzing cost data, which is where data mining is being used frequently today, which is a very practical application. This is what the course textbook focuses on. However, the future of data mining extends far beyond cost data alone and has large implications for various areas, including the development of computerized decision support systems. This will be the focus of the next lecture. I want you to be familiar with both applications because your textbook really only covers how data mining is being used today. But I also think it's important for you to understand how data mining will be used in the very near future. Data mining essentially is the construction of data models that instantiate a machine learning algorithm on specific data elements. The model captures the essence of the discovered knowledge and helps us in our understanding of the world. Oftentimes, these models are predictive. For instance, data mining models have been applied to healthcare data to predict readmissions, risk of disease, and efficacy of medications. Modeling is the process of turning all that data into some structured form of model that reflects the supplied data in some useful way. The aim of modeling is to explore the data to address a specific problem by modeling or mimicking the real world. For instance, a lot of research has been done in modeling the way in which we make decisions. Machine learning algorithms that use artificial intelligence develop models that closely represent how a human would make a decision. The same methods can be applied to healthcare data where we attempt to model decision making. For instance, we might want to develop a model to predict drug relapse in patients with a history of drug addiction. The machine learning algorithm using artificial intelligence will look at all of the data elements to come up with a decision on the likelihood of whether a patient will relapse. Unfortunately, no model can perfectly represent the world. For instance, we might find that our model predicts a patient will relapse even if that patient does not have a history of drug addiction. In the real world, we would never make this mistake, but due to the rules of governing the machine learning algorithm, such mistakes are possible. To ensure that the model is constructed in such a way to limit such mistakes and represent the real world as closely as possible, there are a set of 8 steps that can be followed. First, you must have a clear understanding of the data in the business of healthcare. If you do not know what the data mean, it is likely that your model will not make sense. Second, you must partition your data into training, validation, and testing datasets when building, tuning, and evaluating your model. This way, 3 different sets of data are used to validate your model. Third, build multiple models and compare their performance. You may find that you favor one model, such as a neural network, but that model may not be the most effective. Therefore, comparing the performance of multiple models will yield the most effective end product. Fourth, if you end up developing a perfect model, something went wrong. Healthcare data is messy and complex. It's unlikely that you will develop a model that makes perfect decisions. The laws of probability suggest otherwise, that your model will at times make mistakes. Fifth, don't overlook how the model is to be deployed. Some of the algorithms are very difficult to employ. For instance, neural networks are a black box and difficult to automate into a system. However, rule-based algorithms such as decision trees are very simple to deploy. Sixth, when constructing your models, they should be repeatable and efficient. That is, if you were to take a different set of data and apply your model, you should get similar results. Also, your model shouldn't take 3 days to run. It should be almost instantaneous. Otherwise, it's unlikely that it can be implemented in a healthcare setting where everything is fast-paced. Seventh, let the data talk to you, but not mislead you. If you are certain that the results of your analysis are doubtful, you should question the results. Don't assume that the results are the truth. Test it again, and again. Lastly, after you constructed your model and tested it, communicate your discoveries effectively and visually. There are many tools available for data mining and constructing models. One of the most powerful tools include SAS Enterprise Miner. The platform is powerful and relatively easy to use. Weka is an open source platform that supports the development of a variety of algorithms. Rattle is a package available in the open source analytics environment R and is also powerful and diverse. Rattle also supports predictive modeling markup language for deploying data mining models. There are many other applications available. As stated, R has a package called Rattle that offers a graphical user interface for navigating through what is known as the CRISP-DM data mining process. It is quite easy to use and has plenty of documentation to assist in navigating through each step. Particularly, there's a textbook by Williams called Data Mining with Rattle and R, The Art of Excavating Data for Knowledge Discovery, that is written for an audience with little to no experience using data mining algorithms. It's very informative and offers practical solutions for carrying out a data mining task. Data mining has some terminologies you should understand. A data set is a collection of data. Oftentimes a data set will have multiple columns and many rows. In mathematical terms, this is referred to as a matrix. In database terms, this would be referred to as a table. The observations make up the rows of the data, while the variables make up the columns. The dimension of a data set is the number of observations or rows by the number of variables or columns. Input variables include measured data items. They can take on many different forms, either text, numbers in ordinal, nominal, interval, or ratio. Other names for input variables include predictors, covariates, independent variables, observed variables, or descriptive variables. An example would be systolic blood pressure, diastolic blood pressure, medications, weight, age, gender, and so on. Output variables are those that are influenced by the input variables. They're also known as target, response, or dependent variables. An example might be a diagnosis of hypertension. We build models to predict the output variables in terms of the input variables. So, if we were given data, and this data includes systolic blood pressure, diastolic blood pressure, medications, weight, age, and gender, we could use that data as inputs for predicting the output of a diagnosis of hypertension. There's one caveat. Some data mining models may not have any output variables. These are referred to as descriptive models, and an example is clustering. We will get there in just a moment. Identifiers are unique variables for a particular observation. They may include a patient's name or patient ID. Categorical variables are ones that take on a single value and are discrete. They can be nominal, where there's no order to them, for example, eye color, or ordinal, where there is natural order, for example, age groups. Numeric variables, also known as continuous variables, are values that are integers or real numbers, for example, weight. There are three data sets that are used when constructing a model: training, validation, and testing data sets. The training data set is the data that you use to build the initial models. The validation data set assesses the model's performance that you developed using the training data set. This step helps fine-tune the model as appropriate. The testing dataset applies the refined model and assesses expected performance in future datasets. When developing a data mining model, you start with one large dataset and then partition that into a training, validation, and testing dataset. The partitioning is done by randomly selecting observations to one of the three datasets. The training set typically has more data than the other datasets. For instance, if we take a large data set, we can partition our 3 data sets as follows. 70% of the observations go to the training data set, 50% to the validation, and 15% to the testing data set. The data mining process that is widely accepted is known as CRISP-DM, or Cross-Industry Standard Process for Data Mining. This process includes 6 steps from understanding the business all the way to deploying a model. The slide on your screen shows a description of the 6 steps. The first step emphasizes the business understanding for planning your data mining project so that it aligns with the organization's goals. The second is data understanding so that you can assess the quality of the data and define each data element. Data preparation is next, where you select the relevant data, clean the data up, carry out basic descriptive statistics, and reformat the data as necessary. Modeling is next, where you construct a data model or several models. Evaluation is the step where you evaluate the performance of each of the models that were constructed, and then choose the best performing model. Last is deployment, where you determine how you will deploy your model and present the findings to the necessary parties. The CRISP-DM process relates very well to specific data mining tasks. For instance, business understanding relates to developing questions about the data and data selection. The data understanding step is where we explore the data. The data preparation step is where the data is transformed. The modeling step is where we choose and build a model. The evaluation step is where we validate and test our model. Finally, deployment is where we export the model. When building a model, there are 2 main categories. The first is descriptive models, also known as unsupervised learning. These are models that are constructed when we do not have a target variable, providing a representation of the knowledge discovered without necessarily modeling a specific outcome. An example of a descriptive model is a clustering analysis. Predictive models, or supervised learning, are those that can be deployed when we have a target variable. We can predict the target variable with our given set of input variables. The goal of a predictive model is to extract knowledge from historic data and represent it in such a form that we can apply the resulting model to a new situation. In that way, we are predicting the occurrence of an event of interest. The historic data will already be associated with the outcome, and then we can learn to make this association on future data. Common predictive algorithms include decision trees, boost, and neural networks. If we find that our model is effective and ready for deployment so that it can be used in real time, we can use software for automating the deployment process. As already stated, R has a method of deploying data mining models using a language called Predictive Modeling Markup Language, or PMML. It is an XML-based standard that is supported by many major commercial data mining vendors and many open-source data mining tools. The question you may have is, how can data mining be used in healthcare? Well, largely, data mining algorithms can be adopted to drive the development of clinical decision support systems. There are really 2 main types of clinical decision support systems. The first type is based on human-generated rules. For instance, we know there may exist interactions between certain drugs. A rule can be generated that when a specific drug is prescribed to a patient with another drug, an alert should be generated to the provider to notify the provider that a potential interaction can occur. This type of decision support is very common. Another type of decision support are based on rules that are generated by a machine or computer. This is where data mining algorithms can be adopted. For example, based on patients' clinical history and recent lab results, a machine-generated rule might be triggered to indicate to the provider that this patient has a higher likelihood of having cervical cancer. Therefore, the provider may suggest additional screening for the patient. This is where data mining has great implications for the development of clinical decision support systems. In one article, they described data mining in clinical decision support systems. The article, as linked on the screen, provides a lot of examples on how data mining algorithms have been adopted for developing clinical decision support systems, or CDSS. Some examples include computer-aided diagnoses of breast cancer based on ultrasound images, screening of prostate cancer based on serum protein patterns, identification of hospitals with potentially quality problems based on risk-adjusted death within 30 days of non-cardiac surgery, and flat foot functional evaluations using a gait analysis. These are just a few examples on how data mining can be used to support clinical decision support. Now we're going to look at some examples of exploratory data analysis. The Case Mix Index Analysis, or CMI, is a common method for aggregating data about Medicare Severity Diagnostic Related Groups, or MS-DRGs. A CMI can provide information about how frequent certain MS-DRGs occur to better understand the mix of patients that are treated by a hospital. Although CMI analysis was originally developed for Medicare patients, analysts have found utility for other patients as well. To calculate the CMI, you need to have access to MS-DRGs for a hospital and to calculate a weighted average of the MS-DRGs relative weights using the following steps. I first want to explain that the relative weights are calculated based on the severity and cost of treating specific conditions. The cost includes resource and human, for example, wages, associated costs. The weights can be understood as the average severity cost of a patient. So if a DRG has a weight of 0.5, that would mean that patients with that diagnosis are half the cost and severity of the average patient seen. A weight of 2 would mean that patient has a cost and severity about twice as high as the average patient seen. Thus, a higher MS-DRG weight indicates a more severe and more costly patient. To calculate the case mix index, you must first multiply the number of discharges the number of discharge cases in each MS-DRG by the relative weight of that MS-DRG to obtain a total relative weight for that particular MS-DRG. Next, sum all the relative weights for each MS-DRG that was calculated from step 1. Next, sum the number of discharges across all the MS-DRGs chosen to be evaluated. Last, divide the total relative weights that were calculated from step 2 by the total number of discharges from step 3. This will give you an average of MS-DRGs relative weight for all the discharge patients selected. Let's say that we are interested in obtaining a case mix index from the 7 selected MS-DRGs. If you want more information about what these specific MS-DRGs represent, I recommend that you download the PowerPoint presentation, and each of the codes is linked to a description. For example, if I click on the MS-DRG code for 181, I'll be directed to a website that specifies the code as respiratory neoplasms with CC. The CC stands for complication or comorbidity. I'll talk more about the CC, MCC in later slides. Regardless of what the codes mean, let's say that these were the codes you were interested in using for calculating the case mix index. For each of the MS-DRG codes, you would count the number of cases that were discharged from the hospital. So for MS-DRG 181, there were 10 cases discharged. Each of the MS-DRGs are assigned a relative weight based on the disease severity and cost. For those MS-DRGs that are selected, you can conclude that based on the relative weights, that code 192 is the least severe, while code 286 is the most severe. If you multiply the relative weight by the number of cases for each MS-DRG, you get a total relative weight for each code. Next, you have to sum the total of the relative weights and divide that number by the total number of cases. So in this case, the sum of the total relative weights is 107.493, and there are 82 cases. So if we do the math and take 107.493 divided by 82, you get 1.311, which represents the case mix index. So what does the case mix index mean? Well, it can provide a basis for the severity of diseases for patients that are discharged and treated by a hospital. The case mix index is often tracked over time to determine if there are any fluctuations in patient severity, as this may affect cost or staffing. Organizations often use a threshold of a 2% change, either up or down, in a given time frame as a trigger for carrying out a comprehensive evaluation. One thing that must be recognized is that the DRG weights change each fiscal year. However, there is DRG grouper software that can be utilized for grouping the old and new DRGs together. There are other measures than just case mix index that can be used for analyzing the MS-DRGs. The severity of illness in a particular population can be analyzed using the overall percentage of a population that has complications of comorbidity or major complications or comorbidities. An MS-DRG can be associated with a CC, MCC, or without either. The combination of a CC and or MCC with an MS-DRG can provide some indication of disease severity. A complication is a medical condition that arises during an inpatient hospitalization, such as a postoperative wound infection. A comorbidity is a pre-existing condition that, due to its presence with the specific condition, causes an increase in length of stay by at least 1 day in approximately 70% of the cases. A major complication in comorbidity is the most severe of complications or comorbidities that place a patient in the highest severity category within the MS-DRG system. Hospitals can determine the percentage of patients discharged within each of the different severity levels of each MS-DRG by looking at the CC and MCC frequencies. Comparing the facility percentages to national percentages can provide a hospital with some indication as to whether the patient population for an MS-DRG is different than the national average. For instance, a hospital's percentage in a higher weighted MS-DRG may be because the facility has a nationally known transplant surgeon on staff that specializes in high-risk transplants. The percentage of discharges in a particular MS-DRG member of a pair is calculated as the percentage of CC cases. So to calculate this percentage, count the number of patients with a specific MS-DRG and a complication and comorbidity, and divide that number by the sum of the number of patients with that same MS-DRG and complication and comorbidity, plus the number of patients with that same MS-DRG but no complication and comorbidity. Then multiply that by 100 to get a percentage. Triplet comparisons are made by determining the proportion or percentage of complication and comorbidity cases out of the patients with CC, MCC, and no CC. You can also change the numerator and determine the proportion of MCC cases. For this comparison, you start off the same as above, but by counting the number of patients with a specific MS-DRG and with complications and comorbidities, and divide that number by the sum of the number of patients with that same MS-DRG and major complications and comorbidities, plus the number of patients with that same MS-DRG and complication and comorbidities, plus the number of patients with that same MS-DRG with no complication and comorbidities. Then multiply that number by 100 to get a percentage. Let's work through an example for calculating a pair percentage for determining the percentage of MCC cases for patients with a major skin disorder. The MS-DRG for major skin disorder with MCC is 595, and the MS-DRG for major skin disorder without MCC is 596. Let's say you found that there were 8 patients with the MS-DRG of 595, major skin disorder with MCC, and 22 patients with the MS-DRG code of 596, major skin disorder without MCC. In our calculation for determining the percentage of MCC cases, we take the number of MCC cases, which is 8, and divide that number by the sum of the MCC cases, which is 8, plus the number of no MCC cases, which is 22, which equals 30. So 8 divided by 30 is equal to about 0.267. And if we multiply 0.267 by 100, we obtain the percentage of MCC cases for major skin disorder at 26.7%. However, we may also want to know not just the percentage of MCCs or CCs within a given MS-DRG, but also the total percentage of CCs and MCCs with a given MS-DRG. To calculate this, we must use the MCC Capture Rate. The The CC capture rate is the number of patients with complications and comorbidities compared to all the patients in the population, while the MCC capture rate is the number of patients with major complications and comorbidities compared to all of the patients in the population. The CC-MCC capture rate is a valuable tool in measuring overall severity of patients served by a hospital or physician. So to calculate the CC-MCC capture rate, you would first count the number of patients with CCs plus the number of patients with MCCs in a given MS-DRG, and divide that number by the total number of all patients with that given MS-DRG. Then multiply that number by 100. If you're only interested in the CC capture rate, you would first count the number of patients with CCs in a given MS-DRG, divide that number by the total number of all patients with that given MS-DRG. Then multiply that number by 100. This MCC capture rate is calculated the same way by counting the number of patients with MCCs in a given MS-DRG, and divide that number by the total number of all patients with that given MS-DRG, then multiply by 100. When conducting an MS-DRG analysis, an analyst is often required to examine increases and decreases in the average weighted values over time. This may be a monthly or quarterly requirement with the sole purpose of identifying not only if there is a significant increase or decrease in weighted averages, but also why a change may occur. The general rule of thumb is that any increase or decrease in an average weighted value that exceeds a 2% change is subject to further analysis. That is, you may investigate further why a significant shift in the average weighted value is occurring. A shift of greater than 5% is considered critical. The reason for significant shifts in average weighted values is often due to changes in the patient case mix. That is, more patients are seen with a specific MS-DRG. Common reasons for more patients seen with a specific MS-DRG includes seasonality. If it is a flu season, it's likely that the MS-DRG for gastric diseases would increase. Changes in an area's healthcare environment can also be causative. If a hospital is opening or closing a service line, for instance, this may cause a significant change in the reported MS-DRGs. Changes to medical staffing with either a loss or gain of physicians may cause a shift. Changes to Medicare contracts can also contribute. Coding changes due to alterations in the coding rules regarding the way MS-DRGs are handled may be a reason, or new coding staff, or changes to a coding assignment could cause variability. Regardless, it is the analyst's job to investigate these shifts further so that conclusions can be made to explain the significant shift in average weighted values. There are other factors that can influence MS-DRGs. Since the implementation of the DRG system, hospitals had the opportunity to receive additional payments when complications occur during the treatment of a patient. However, there's a conflict in this reasoning because it doesn't make a lot of sense to pay extra for potentially preventable complications that occurred during the patient's stay. For example, if a patient is admitted to the hospital and is injured from a fall, whose responsibility is it to pay for this injury? Therefore, this sparked the development of the Present on Admission (POA) indicator to indicate those conditions that arose following the admission. When a condition is not POA, it is termed a hospital-acquired condition, or HAC, and will not be included in the calculation to increase the level of MS-DRG severity. The table on the slide lists the POA indicators along with the descriptions and effects on payment. The POA indicator is a Y for yes. This indicates that the diagnosis was present at the time of inpatient admission, and therefore CMS will pay the CC or MCC DRG for those selected hospital-acquired conditions that are coded as yes. If the POA indicator is a no, N for no, the diagnosis was not present at the time of inpatient diagnosis. Therefore, CMS will not pay for the CC or MCC DRG for those selected HACs. A U is for unknown and indicates that documentation was insufficient to determine if the condition was present at the time of the inpatient admission. However, CMS will still not pay the CC or MCC DRG for those selected HACs. This is one reason why proper documentation is important for receiving adequate payments. A W is for clinically undetermined and indicates that a provider was unable to clinically determine whether the condition was present at the time of inpatient admission. In these cases, CMS will pay the CC or MCC DRG for those selected hacks. Lastly, a 1 is for unreported or not used and indicates an exemption from POA reporting and will not affect payment. The hacks that affect payment by CMS for the fiscal year of 2013 are listed in your textbook on the final pages. I recommend that you take a look at these if you're interested in knowing precisely what types of conditions are considered hospital acquired. Another diagnosis-related group is the all-patient diagnosis-related groups, or APDRGs. This is an enhanced DRG system to cover all non-Medicare patients, including children and neonates. In fact, some states use this system as the basis of their Medicare payment and is referred to as the New York Grouper. However, the APDRG has been enhanced to include severity of illness and risk of mortality of patients, and was renamed the All-Patient Refined Diagnosis-Related Groups, or APRDRGs. The link at the very bottom of the screen contains a lot more information about this transition. The APRDRG includes 4 subclasses within each DRG that divide patients into groups of disease severity and risk of mortality. Age, CC, and MCC groupings are removed and substituted with 2 sets of 4 subclasses. One group of 4 subclasses for severity, and one group of 4 subclasses for risk of mortality. The subclasses are coded as either minor, moderate, major, or extreme. The APR-DRG has 3 components, each separated by a dash. The first component is the base DRG code. The second is a digit from 1 to 4 to describe severity, and the third is a digit from 1 to 4 to describe risk of mortality. For example, an appendectomy has a DRG code of 225. If the disease severity is minor and the risk of mortality is minor, the APR-DRG is 225-1-1. Lastly, each APR-DRG has a relative weight assigned that reflects the severity of illness and risk of mortality for patients assigned to that category. These relative weights do not have a relationship to the relative weights assigned to an MS-DRG. However, a case mix index can be calculated for an APR-DRG using the same method for the MS-DRG. Another disease-related grouping system are the Ambulatory Patient Classifications, or APCs. These are groups used by CMS to categorize and pay for hospital outpatient visits under the Hospital Outpatient Prospective Payment System, or HOPPS. A challenge in analyzing APC data is that there can be more than one APC group associated with an outpatient visit. Therefore, this analysis can be a bit more of a challenge than the MS-DRG analysis. Another challenge is that the APC groupings are changed by CMS yearly. The link at the bottom of the slide provides some additional information about APCs that you may find helpful. APC data is often analyzed based on the frequency that a code occurs. The table on the slide depicts one of these frequency reports. As you can see, the first column contains the specific APC code, and the second column has a short description. You can ignore the SI column. In addition, the relative weights assigned to each APC and the payment rate is provided. In the example shown on the slide, the volume of visits is shown next for a specific hospital. When the volume is multiplied by the payment rate for each of the APCs, then you can calculate the total payments. Finally, the relative volume of the hospital can be compared to the national Medicare volume for the previous year, and these tables are really helpful for yearly trending, so future revenue projections can be done by substituting the previous payment rates with new payment rates. APCs can also be analyzed to describe the outpatient population in just a single number. The number is called the service mix index. The calculation is essentially the same as the case mix index, where you multiply the relative weights for the volume for each APC to obtain a total weight. Next, sum up all of the total weights and divide the number by the total volume to obtain an average total weight, also known as the SMI, or Service Mix Index. For the example shown on the slide, the SMI is about 1.7. Therefore, on average, their volume of patients is largely from level 4 hospital clinic visits. I determined this by looking at how close our calculated SMI is to each of the relative weights for the APCs listed. Because 1.7 is close to the relative weight for a level 4 hospital clinic visit at 1.8, we can conclude that, on average, patient visits are largely related to level 4 hospital clinic visits. There are a couple other ways APCs can be analyzed. APCs can be used to find missing charges using a charge analysis. A charge analysis is carried out by determining the consistency in the data. APCs should coincide with specific HCPCS and CPT codes. If they are not, this may be a marker for errors in data entry. For a charge analysis, you essentially create a frequency table by counting how often an APC code occurs with HCPCS or CPT codes in order to determine if data was entered correctly. Lastly, APCs can be used for analyzing patterns of care. If you wanted to only evaluate a specific sample of patients based on the type of visit, APCs can be very beneficial. For instance, you can use APC 0616 as a way to determine which patients were a level 5 emergency department visit. A utilization pattern analysis using bell-shaped curve graphs is one way in which you can compare and display any group of data that has 2 or more points. Let's say you have a physician called Dr. X that practices in internal medicine, and you wanted to compare Dr. X's volume of new patient visits using evaluation and management codes, or E&M codes. These codes are standard guidelines for determining type and severity of patient conditions. As you progress from code 99201 to 99205, the type of patient visit is coded at least to most complex. If Dr. X saw 636 patients in fiscal year 2006, we can use the E&M codes to segregate the type and severity of patient visits and compare these codes to that of Medicare's national count. For the least severe, Dr. X saw 24 patients, while there were 14,530 Medicare patients. You can continue on with more severe and complex patient visits and compare Dr. X's numbers to the national count. To normalize the data to compare Dr. X to the national count, we can convert each number to a percentage. So, for the least severe patient, Dr. X saw 24 out of 636. When we do the math, 24 divided by 636 is equal to about 4%. We can do the same for the national counts and take 14,530 least severe patients divided by the total 1,649,388, which is about 1%. If we graph these percentages for both Dr. X and Medicare, we can compare each of the E&M codes. Looking at the graph, we find that Dr. X has a greater proportion of patients with the E&M code of 99203, a detailed new patient visit, while Medicare has a greater proportion of patients with E&M codes 99204, a comprehensive new patient visit, and code 99205, a complex new patient visit. AAPC has an online tool that will create these graphs for you using the newest Medicare data for benchmarking. The link is found at the bottom of the slide and is the first link listed. The second link is to the CMS webpage, where there is a detailed description of the E&M codes, particularly related to the differences between each of the types of patient visits. There are specific objectives a patient visit must meet in order to be placed in a particular category. The next type of analysis we're going to cover is the relative value units, or RVU analysis. RVU is a measure of resource intensity that is assigned to CPT codes. The units compare the relative difficulty and costs associated with different procedures. The total RVU, or TRVU, is really a combination of 3 subunits: physician work, WRVU, practice expense, PERVU, and malpractice expense, MRVU. Thus, RVUs can be used to evaluate work volumes, patterns, and expenses in physician practices, hospitals, as well as better quantify the work performed by outpatient service lines. There are a few interesting things you should know about RVUs. First, Medicare made RVUs the basis of the Medicare fee schedule. The fee schedule is based on the Resource-Based Relative Value Scale, or RVS. The RVU values are weighted geographically using a Geographic Practice Cost Index, or GPCI, and multiplied by a national conversion factor to determine the Medicare approved amount for each procedure code. CMS offers a toolkit to look up physician fee schedule based on each HCPCS code. For context, the formula for calculating the amount for a Medicare payment for the year 2013 is shown on the slide. RVU data can be analyzed for specific physician, clinic, specialty, or service line. One way RVUs are used is to assess physician productivity using the work RVU, or WRVU. It provides a comparative value for work across specialties. However, this measure is only for physicians' clinical work and not the physician's overall work on behalf of the physician practice or hospital. Thus, research work, management duties, and teaching responsibilities are not accounted for. To begin, an analyst must know the full-time equivalent, FTE, associated with clinical work. This is called the clinical FTE, or CFTE, and should be calculated for all providers. For example, a physician who works 48-hour days, a physician who works 4 8-hour days, does not do hospital rounds, and does not take call, would have a CFTE of 32 hours, divided by 40 hours, equaling a CFTE of 0.8. This is important if you were to compare productivity across different providers. The table on this slide shows the physician production productivity by CPT ranging for procedures, encounters, and WRVUs for Dr. Number 1 of My Town Family Practice, South Carolina. As you can see, Dr. Number 1 conducted 698 procedures with the CPT code ranging from 99200 to 99499, which accounted for 30% of all procedures. These procedures were carried out in 449 patient encounters, or 39.5% of all patient encounters. The physician work RVUs, or WRVUs, for each of the CPT codes in that range accounted for a total WRVU of 1,035.06, or 47.62% of all the work RVUs. We can continue down the line of CPT codes to gain a further summary of what type of work Dr. Number 1 was doing. By doing so, we discover that Dr. Number 1 did a total of 2,248 procedures in 1,139 patient encounters, equaling a total work RVU of 2,173.39. If we wanted to compare Dr. 1 to other doctors, we could do so using the totals we calculated for each doctor and their CFTE status. Using this data, we can calculate the average number of procedures per encounter for each doctor by taking the number of procedures divided by the number of encounters. So in the case of Dr. Number 4, we would take 708 procedures divided by 342 encounters, which equals an average of 2.07 procedures per encounter. We can calculate the average work RVUs per encounter as well. Again, using Dr. Number 4, if we take the work RVUs of 732.41 divided by the encounters of 342, we get an average work RVUs per encounter of 2.14. Finally, the average work RVUs per procedure can be calculated the same way. So Dr. Number 4 had 732.41 work RVUs divided by 708 procedures equals 1.03. If we wanted to normalize the procedures, encounters, and work RVUs relative to the CFTE status of each doctor, we can do that as well. Since Dr. Number 4 only works a CFTE of 0.4, we would take the work RVUs and divide that number by the CFTE. So Dr. Number 4 has a work RVU of 732.41, and if we divide that by the CFTE of 0.4, we obtain the value of 1,831. If we compare that work RVU to other doctors, we find that Dr. Number 4 is performing quite well despite part-time employment. That is, Dr. Number 4 is performing better than Dr. 2 and Dr. 3. However, Dr. 1 earned their name by blowing everyone else out of the water. The CFTE status allows us to compare the productivity of each doctor. If we didn't use the CFTE, we would erroneously conclude that doctor number 4 is underperforming based on the raw values alone. Physician practices can evaluate contracts that pay by a set dollar amount per RVU. If they know the practice's average cost per RVU, contracts that pay higher dollar value per RVU than the average cost per RVU have the greatest chance at creating profit. Therefore, the average cost per RVU is also referred to as the break-even conversion factor, or BECF. To calculate the average cost per RVU, you must follow these steps. First, list all the CPT codes used by the practice in a spreadsheet, along with the associated RVU from CMS for physician work, practice expense, and malpractice expense. Weight each of these components by the appropriate GPCI for the location of that practice. Next, total the RVU components for each code. Next, list the frequency of each CPT code used by the practice within a set time frame and multiply the frequency by the total weighted RVU for each code. Total the RVUs produced for that period. Next, obtain the amount of the total expenses for the same time period from the statement of revenue and expenses. Divide the total expenses by total RVUs to determine the average cost per RVU. Finally, calculate the cost associated with any CPT code by multiplying the average cost per RVU by the relative weight for that CPT code. In addition to the average cost per RVU, other measures can be compared to RVUs. These include physician compensation per work RVU, which shows how much a practice pays the provider staff, malpractice expense per MRVU, which shows the cost of malpractice insurance coverage per RVU that is produced, and overhead per PE RVU, which shows the practice's expenses per RVU. The break-even conversion factor is the same as the average cost per RVU. To conclude, I just want to mention that exploratory methods are numerous and relatively simple. Simple math and graphics can go a long way in analyzing administrative and cost data. These analyses can be very beneficial for benchmarking and trending for future projections. However, the methods presented here are not what is typically understood as data mining. Your textbook really doesn't go into a lot of depth into what in computer science is known as knowledge discovery using data mining algorithms. These methods will be the topic of the next lecture.